Thank you all for attending, and welcome to my presentation on multi-constellation ARAIM exploiting satellite motion. So when I started working on this topic, I was still at Illinois Tech, then I moved to the University of Arizona where it was way too hot. And I'm now at Virginia Tech, very happy to be there, of course, obviously. And so I wanted to tell you about this work and this paper in particular. We had many iterations over the years on this topic. And so you're probably gonna see that in the slides. And what I'm gonna present today is the first third of the presentation is going to be some background on ARAIM. Then I will talk specifically about the content of the paper. And the last slide will be on what we've been doing since we submitted the paper. So, Advanced Receiver Autonomous Integrity Monitoring, or ARAIM, it's a research effort that started under the 2004 EU-US Cooperative Agreement on Satellite Navigation. Basically, we wanted to figure out how much benefit we could draw from combining GPS and Galileo in terms of guaranteeing navigation safety. And so there are three major components of advanced RAIM over the existing GPS-based single frequency RAIM that is currently operational. The first one, obviously, is an increase of the number of satellites because we have satellites from both GPS and Galileo. The second is that we are using dual frequency measurements so that the impact of the ionosphere is pretty much eliminated. The ionosphere being the biggest source of error for single frequency implementations. And third, we're using an integrity support message. This will carry integrity parameters, and it will facilitate the incorporation of emerging constellations such as Galileo, whose level of integrity is still maturing. It's quickly evolving right now. And so now we have a way to quickly update those integrity parameters and to do that online without having to basically work on the actual hardware on the receivers. We can also incorporate this way major upgrades of the constellations, and we've had a couple of these upgrades for GPS over the past 20 years, so it will be really useful. So the primary objective of ARAIM that I will be focusing on today is to provide worldwide en route navigation and vertical guidance of aircraft down to 200 feet altitude above the runway. That's what we call meeting the LPV 200 requirements. There are other objectives in ARAIM that I won't be talking about today. They include increasing GNSS resiliency and then providing service in applications other than aviation. All right, so for the background, let's start by defining some navigation metrics. I'm only going to focus on the major navigation performance metric that we're considering in ARAIM. There are others that we are actually using. And this is described in more detail in the paper. So accuracy is the most intuitive performance metric. It kind of represents a performance 95% of the time, whereas integrity is a 7-9 number in this work. And so integrity is defined based on multiple parameters. And to explain that, let's take the example of an aircraft approaching a runway. I hope you can see my laser pointer here. And so the FAA defines an alert limit requirement volume, a cylinder in this case, within which it is safe for the aircraft to be. And so under low visibility conditions, because we're using GNSS to navigate and because these GNSS measurements are not perfect, there is a risk that the aircraft is outside of the box when we think that, or of the cylinder, when we think that it is inside. If I focus on the vertical direction, I can draw the probability density function of the vertical positioning error, and the risk of being outside of the cylinder is the integrity risk. Now, because the risk requirement is 10 to the minus 7, it's much lower than the risk of having a fault, which is approximately 10 to the minus 5. And so we have to do something against these faults. We have to detect them. And now the best we can do in terms of risk evaluation is to consider the worst case undetected faults. If we don't detect a fault, it doesn't mean that there is no fault. It just means that we haven't detected it. We haven't seen it. And so the best we can do is, let me move that thing around here. Okay. All right, the best we can do is to derive a bound on the integrity risk. I hope you can see that part of my chart in the upper right chart, part of the chart. All right, so deriving a bound on a risk or on a probability is straightforward. I can just say, let's take a bound on one. But of course, if I assume my risk is 100%, I will never be using my system. It's really, I will always be assuming it's unsafe. So we have these conflicting requirements of continuity and availability that force us to derive tight bounds on the integrity risk. Okay, and the whole challenge in this work is to derive these tight bounds that meet the integrity risk requirement, but also continuity and availability risk. And of course, this has to be done in a computationally efficient way. So very briefly, let's see how we do positioning in this work. Most of you are very familiar with that, so I will go very fast. As you all know, as most of you know, we need 4 measurements to determine the 3D position of the user together with the receiver clock bias, because the receiver is not time synchronized with the satellites. So we need 4 satellites to get a position fix. We can stack these, I'm introducing some notations here. We can stack these measurements into a measurement vector Z and express our linearized measurement equation, Z equals HX, where H is my observation matrix. It's a lot of notation, but it won't be too complicated. And H is made of the line of sight vectors, the unit line of sight vector to each one of the satellites, and a column of 1s for the receiver clock bias. And my states are the 3D position and the receiver clock bias. Of course, these measurements are not perfect. They're impacted by what we call nominal errors, nominal because they impact measurements all the time. They include the parts that account for the random part of the errors, which we can deal with using overbounding theory. Overbounding is a building stone of integrity analysis. It lets us model errors whose distribution is pretty complicated. Empirical distributions, we couldn't put a name on them. They don't have to be Gaussian, but we can use Gaussian models using overbounding theory to account for these errors. So we could have an entire seminar on overbounding, but for now, this is the model that I'm using. Again, check the overbounding theory to see why we can make that assumption. In addition, in ARAIM, we have this V vector term here that I label as non-Gaussian error. What this accounts for are these sources of errors that are just difficult to model. For example, we have the signal deformation that is going to impact different receiver antennas and different user receivers differently. And so we can't calibrate that for all receivers that are around. So we simply have that bounded bias. The only thing we know about this vector is that its elements have a maximum value. Okay, we don't know how they change over time. We don't know if they are random or not. So we have this bounded bias term. And then the part that is interesting from a RAIM perspective is the fault vector. Faults are large errors that are not obvious. For example, the most common ones are excessive acceleration of the satellite clock. And these are specified to occur no more than 3 times per year for GPS. That's about once every 10 years for a single satellite. So 3 times per year doesn't seem like a very likely event. But if you think about crashing a vehicle 3 times per year because of GPS, then it becomes pretty substantial. So we have to acknowledge the presence of these faults and try to detect them. And so the FAA, in response to these faults, has developed augmentation systems. We have the ground-based augmentation system where the communication link is at the ground at a few airports around the US. And there are these ground-based augmentation systems in other countries as well. And the space-based augmentation system where the communication link is a geostationary satellites. There are limitations to these systems. First, the cost of the infrastructure, installation and maintenance. Think of all these reference stations, a geostationary satellite, all of that is expensive. Then we have a stringent time to alarm requirement. So if a fault occurs, It has to be detected at the ground stations. The alert has to be sent to the communication link and down to the user. All of that within 6 seconds. All of that with a risk smaller than 10 to the minus 7. This is extremely challenging to achieve, even more challenging to certify. And then finally, none of these systems are worldwide. An alternative solution would be to use redundancy. So we saw earlier that we needed 4 satellites. If we have a single constellation, we need 4 satellites to get a position fix. Still, for a single constellation, if we have 5 satellites, we can start doing detection. And I will give you an example of a detector in a couple of slides. So if our aircraft is approaching the runway and if a fault is detected, we can simply abort the approach and that will improve integrity. That's the safe thing to do. All right, you can see that in this implementation, because we're using redundancy, there are no reference stations, there is no communication link that is needed. That is why we call this receiver autonomous integrity monitoring, RAIM. Okay? Now, if we have more redundancy, if we have 6 satellites available still for a single constellation, then we can not only detect single satellite faults, but we can also remove them or exclude them from the solution. So if we started an approach, we detect a problem, we remove the problem, we can continue the approach. So these concepts of detection for better integrity, exclusion for better continuity, these concepts were developed in the early 1990s. But at the time, there was not much in terms of redundancy because GPS was the only constellation available. Now we're entering a new era in GNSS with the modernization of GPS, the redeployment of GLONASS, and the emergence of Galileo and Beidou. We can have 25 to 35 satellites available at all time at any location on Earth by 2025. In this work, we're going to focus on GPS Galileo. And as part of the ARAIM group, we've been looking at different trade-offs. Of course, if we have more satellites, we have more measurements to provide better accuracy and more redundancy for better integrity monitoring. But on the other hand, if we have more ranging sources, more measurements, the probability of faults becomes higher, and the probability of detecting the faults and of interrupting missions because of detection is becoming higher. And so my continuity risk becomes higher. So there's a trade-off. Of course, you're going to say, why don't you do exclusion? Okay, let's do exclusion to mitigate loss of continuity. But now I expose myself to the risk of wrong exclusion, which is going to increase the integrity risk. So there's really a balance. And on top of that, you can have satellite outages because we need to maintain these satellites in their predefined slots within the orbit. And so we have these occasional station keeping maneuvers. So outages exist and are going to impact our performance. All of that has been studied now for years and part of our analysis in ARAIM. All right. The last point I want to make here on ARAIM, because I won't have to talk about it when I talk about the content of the paper, is about our baseline algorithm. And again, I'm only going to brush the surface here. And so the challenge in this ARAIM, the airborne algorithm, is to evaluate risk, or what we call the probability of hazardously misleading information, HMI. That probability of HMI is defined as a joint probability of the estimation error exceeding the alert limit and the test statistic being smaller than the threshold. In other words, it is the probability or the risk that the aircraft is outside of the safe alert limit box when we think that it is inside and there is no alert. So there's nothing to tell us that something is wrong. If I consider a set of mutually exclusive exhaustive hypotheses of a fault on satellite 1, or a fault on satellite 2, or a fault simultaneously on satellite 1 and 2, then I can rewrite my probability as a sum of probabilities over all of these hypotheses. This is expressed here with this conditional form, given hypothesis HI, again, of fault on a subset of satellites, times the probability of fault. And that's pretty much the only thing we're able to determine conservatively, the probability of occurrence of these faults, because they are so rare. So we have a number to put on this probability. All right, so the ARAIM baseline algorithm that you can find in the milestone documents that are available online and referenced here. They can efficiently deal with single satellite faults, same as RAIM, but also multi-satellite faults, multiple simultaneous faults, even constellation-wide faults. And it efficiently accounts for all of these fault hypotheses. Think about it. If you think of all faulted versus fault-free hypotheses for, let's say, n satellites, you will have 2 to the power n combinations. That can quickly grow large when you have lots of satellites available. Well, we have efficient ways to deal with that, including grouping hypotheses. All right, also part of this airborne algorithm is the detector. So I talked in my risk equation here about the estimation error and the estimator. I'll talk about it again later. Initially, we started with a least squares estimator and it has evolved. And we have our detector. How do we do detection? Well, we selected solution separation, and I will try to explain why. So let's take an example where we have 5 satellites available, okay? And in this example, satellite number 1 is faulted. And so I represent my probability density function of the vertical positioning error. Because of the impact of the fault, that distribution may be shifted. Because I have redundancy, I have 5 satellites, I can compute subset solutions of 4 satellites each. 4 of these subset solutions will have their means impacted and shifted because of the presence of the faulty satellite 1. And the last one, the fault-free, the fault-tolerant solution, will have its mean at 0. And so an intuitive detector is to simply take the difference between the full set solution and each one of the subset solution. Okay, so this is our detector. It is normalized here by the standard deviation of the solution separation. Okay, why did we select solution separation? Well, first of all, we've been looking at the optimality of this detector when we consider a multiple hypothesis approach here. And it turns out that solution separation actually approaches the optimal detector. Secondly, solution separation has important properties in order to guarantee overbounding, okay? Because in this case, our test statistics are linear combinations of the measurements. And that really facilitates application of overbounding theory. That's an advantage over chi-squared approaches that is often overlooked. All right, so this is really the very basic background for ARAIM. But we've gone well beyond that, and as part of the ARAIM group, we've made contributions in many aspects of ARAIM. First of all, as far as measurement error and fault models, there have been theoretical contributions in terms of overbounding theory by Juan Blanc, in terms of fault probability evaluation, and a lot of historical data analysis. That's what it took, years and years, tens of years of data were analyzed to get conservative models of our measurements. On the receiver algorithms part, told you earlier, we are not using a least squares estimator. Instead, we're using an optimal estimator that is designed to minimize the integrity risk. And that made a big difference in terms of ARAIM availability. We have a way to conservatively account for wrong exclusions, for failed exclusion and how they impact integrity and continuity respectively. We have a way to account for outages, how they impact continuity as well. And more recently, we've been working on the problem of how do you compare a punctual risk estimate. That's what the receiver computes. At one time, it computes a risk estimate. But remember or actually I'm telling you, the requirements are specified either per approach or per hour over time. So it takes a little bit of a conversion to compare apples to apples. And we have a rigorous way to account for the exposure time and the time to alarm as part of this computation. And there are many more contributions I don't have time to talk about. All right, so that concludes what I have to say here for my background on ARAIM. And now to take a little break, I suggest that we have a little poll question. A few years ago, we had one of these poll questions in another seminar, and I found it really interesting. And it's on a topic that is close to my research interests. And so the question is, now that we have had an overview of integrity monitoring and how we ensure safety for aircraft, when do you think will we have privately owned, fully autonomous self-driving cars? The car, you know, the type of self-driving that lets you commute while you check your emails. You don't have to worry at all about the road. And we want these autonomous cars with high integrity, continuity, and availability. All right, so maybe we can put up the poll. Rick? Thank you. All right, while you're answering these questions, please do. I'd like you to consider the following points. On the one hand, it took 10 to 20 years of research to get the alert limit box around the vehicle down to 10 meters above and below the vehicle for the aircraft application here. So took a long time. And if you look at the car, of course, you can't afford much more than 1 meter. So there's an order magnitude difference in the alert limit requirement box. Also, self-driving cars, they operate in a much more dynamic environment. You can have trucks passing by and occluding your measurements from your LiDAR camera or even GNSS. But on the other hand, these autonomous cars, they have sophisticated sensor suites, high-resolution maps, high-performance computing. So how does that play in your prediction? Okay. So thankfully, Rick is handling this. I would be in trouble if I had to do this myself. I guess he's giving you a few more seconds. So Rick, you know, you may end the poll whenever you feel. All right. So I don't know if the audience is seeing the numbers, but the largest percentage, 42% of you answered that we would have autonomous cars, fully autonomous cars in 5 to 15 years, which is actually consistent with most of the predictions that I could find online by, I guess, people who work specifically on autonomous cars. There is quite a large percentage that is assuming that it will be in 15 to 25 years, so 33%. And then 80% not before 25 years. So quite interesting. I can tell you that things have changed quite a bit as compared to 5 years ago. And it's nice. We have an educated audience. All right, I think we can keep going. And thank you for these answers. Okay, so we finished the last section by giving an overview of all the great contributions that were made in ARAIM by all of the colleagues and by the working group C. So despite all of these advances, there were still cases where ARAIM was not providing 100% availability. For example, in cases of depleted constellations, if there was an outage in the nominal constellation, the nominal 24 constellations that we use for our performance analysis. So there was still room for improvement. And so what we propose to do is to push the envelope, try to see if we can do even better. And to do this, we explore the potential of augmenting vertical ARAIM. So we focus on vertical. It's one of the most challenging parts of ARAIM. And I will describe what I mean by augmenting. And we'll do that by exploiting satellite motion. Another thing that we wanted to do here was to set the path towards achieving more stringent requirements. So the alert limit that we're considering under LPV 200 requirements is 35 meters along the vertical direction. So that's a pretty large box around the aircraft. So we wanted to see if we could tighten that. And then we would like to push also towards other filtering methods. Can we provide integrity for example, Kalman filtering, so that we could draw the full potential of GNSS inertial in terms of integrity and continuity monitoring. Okay, that is still ongoing work. And I'll try to point out a few specific points about this. Now, we want to go towards filtering, but there is already filtering going on in ARAIM. ARAIM assumes carrier smooth code measurements from a hatch filter. So even though it may not be specific in the documents, the error models in ARAIM assume that we have a Hodge filter that averages out code measurements using time difference carrier measurements. But a Hodge filter is done on a satellite per satellite basis. It does not exploit the changes in geometry. And I'll illustrate that in a minute. And we know that from prior work that geometry changes can provide observability for determining the carrier phase cycle ambiguities. So it could be, if we could exploit changes in satellite geometry, it could be a way to exploit the precision of carrier phase signals. So other filtering methods can exploit satellite motion. For example, if we use a batch or a finite window estimator, or if we use a Kalman filter. I'll try to explain why we went for a batch in a minute. But we considered both. We actually started with a Kalman filter. As I told you, there were many iterations. So the question we ask as part of this paper is, what is the potential performance benefit of satellite motion to ARAIM? And to quantify that, we must design an estimator and fault detector for position, float, cycle ambiguity estimation, and for integrity risk evaluation. We must also derive that in a computationally efficient way if we have the hope that this may one day be used on avionics. And we must define measurement error models over time. All right. Let's take a little bit of distance and just review all of the different GNSS-based technologies that we've seen so far. So I'm using this chart that is inspired from a chart on the Novatel website, which has on the y-axis the alert limit, so the size of the box around the vehicle where it is safe for the vehicle to be. And on the x-axis is the coverage from local to worldwide. And both of these axes are log scales. And so on top, we have en route navigation, final approach and landing, and then ship all the way to autonomous car navigation. And so on top here, you have the technologies that I've mentioned. You have the GPS-based RAIM, horizontal A-RAIM that I won't talk about, that is for en route navigation, satellite-based and ground-based augmentation systems. And here we have what I'm talking about today in red, the vertical A-RAIM. So DFMC stands for dual frequency multi-constellation. We're using GPS Galileo in this work. And the idea is, can we reduce the alert limit, the vertical alert limit of 35 meters nominally to lower values? Let's see. The idea of using satellite motion to achieve what I just mentioned, lowering alert limits, getting better performance, that is nothing new. In fact, the first global navigation satellite system, Transit, was based on Doppler, which exploits the motion of the satellite. This is an equivalent concept here. If we focus on integrity, there are at least two implementations that we can point out here. The first one is the integrity beacon landing system that was developed in the early 1990s. In this application or implementation, there were two ground-based transmitters. Basically, they call them pseudo-lights for pseudo-satellites. And the aircraft was equipped with an antenna on the belly, looking downwards. And as the aircraft flew by those two pseudo-satellites, pseudo-lights, there was a large change in the geometry that was exploited to do fast carrier phase cycle ambiguity estimation, and that provided high integrity. In parallel, this is work that I did for my PhD thesis more than 10 years ago. I was using GPS together with Iridium, so low Earth orbiting telecommunication satellites. And we were using the carrier phase measurements from these. And the idea was the same. So let's look at this chart here, which is an azimuth elevation plot of the sky. This is as if you were sitting on the antenna, looking up in the sky, and you look at the motion of the satellites for 10 minutes. And you would see that the GNSS satellites, they barely move at all, a fraction of a degree, maybe a degree and a half over these 10 minutes. In contrast, the Iridium satellites, they cross large sections of the sky. So we were exploiting this. Notice that in both of these implementations, the satellite motion is a large motion, but from a few ranging sources. Well, when we use GPS Galileo, it won't be the case. We won't have that. We won't have large motion from medium Earth orbiting satellites at high altitude. And so we wanted, before we started working on this topic, we wanted to check that we could actually get some benefit from using multiple satellites, but each one providing a little bit of satellite motion. So we wanted to convince ourselves that we would get a benefit from the accumulated change in geometry. And to do this, we came back to the original, one of the original examples of an RTK paper, real-time kinematic paper by Huang. And he was using this baseline surveying example. And so we replicated that and adapted it to our problem here. So the baseline here is the displacement, vertical displacement. This is a 1D problem. Again, it's more of a theoretical problem to convince ourselves of the foundations of this work. So the 1D problem is the displacement of the aircraft here vertically, while at the same time between time 0 and time 1, the elevation angle to the satellite, so the geometry of the satellite changes. Okay? And you can find the calculation in the paper, and we ended up seeing that the variance of the vertical displacement was, of course, a function of the variance on the measurement error for these two, for the two measurements that were used over time 0 and time 1. And it is inversely proportional to the change in the sign of the elevation, or the difference of those sinus functions. So inversely proportional to the change in geometry, okay? Squared here because we're looking at the variance. That was the result provided by Huang. What we did is we extended this to using multiple satellites. And this is how it showed up, okay? So yes, having more satellites, the impact of having more satellites, these angular variations are going to help us better determine our displacement in this case, or our cycle ambiguities in the more general problem. So that was convincing enough. And so we started working on this. To quantify the performance, let me explain how we use the measurements. And we start from the baseline ARAIM implementation. The reason for that is we want to be able to leverage all of the great advances and developments that were done under the ARAIM project. And so we wanted to stick as close as possible to the ARAIM baseline algorithm. And so what you see here on the left-hand side are the inputs to the ARAIM airborne algorithm. These are carrier smooth code measurement at some time, current time Q for satellites 1 to n, the left superscript. And so we feed that into our optimal estimator, the multiple hypothesis solution separation detector. And at the end, we get our position estimates, fault detection, and even risk prediction. In reality, as I mentioned earlier, we have hatch filters that give us those carrier smooth code measurements. So if you want to go all the way back to the raw measurements, you have to go one step further. And so the hatch filter is going to process those raw code measurements and carrier measurements for each satellite individually. So you have n of these hatch filters. And this is over a period that lets us reach steady state of the hatch filter. So at least twice the smoothing period of the hatch filter. All right. Now I'm going to show you the augmentation part that we did for our batch ARAIM. Instead of using a single carrier smooth code measurement, we are going to use 3 of these measurements at current time, but also 5 minutes ago and 10 minutes ago. And then we also grab the raw carrier measurement at current time, 5 minutes ago and 10 minutes ago. And we are saying that by taking three of these carrier measurements over time, over 10 minutes nominally. By the way, we selected 10 minutes because we were trying to look at what's the minimum period that we can be pretty sure that the aircraft receiver will be active, okay? And 10 minutes seems like a minimum period. It's basically if you take off and have to do a turnaround maneuver and land again, that's your 10 minutes towards the approach. So it's kind of a minimum period that we've assumed for how long the receiver would be on. Okay, so I'm grabbing these 3 carrier measurements over 10 minutes, and I'm saying this is enough to capture the motion of the satellite, okay? And yeah, so it's fairly straightforward. We do the same for all satellites, and everything else So my measurement equation now is augmented. I have more measurements, but everything else is the same. The estimator, the detector, I get my position estimate, fault detection, risk prediction, same as I do with the baseline estimator or baseline algorithm. And I have a byproduct, which are the float cycle ambiguity estimates. So again, I preserve my code noise averaging from the hatch filters, and on top of that, I get to exploit the satellite motion. Okay? Okay, the second important part of quantifying the performance is the measurement error models. And so we won't have to go through all of the sources of errors, but I will focus on one. So what I have here is an expression of my measurements. The raw code, this is iono-free, we have dual frequency in ARAIM, for a satellite I, left superscript at time k. And it's expressed here as a function of the aircraft position, receiver clock bias. We have cycle ambiguities, this unknown bias that is impacting carrier phase measurements. And then we have sources of errors, tropo, satellite clock and orbit ephemeris, multipath, receiver noise, and then the bounded bias that I mentioned earlier. Okay, so in the paper, we look at each one of these sources of errors. And the challenge in having error models, in deriving error models in this work is, one, they have to be consistent with the ARAIM error models. So for the snapshot application, and two, they have to conservatively account for the change of the error over time. How did we do this? Let's take an example. For the satellite orbit and clock error, we expressed it as a bias plus a gradient over time, plus some residual error that is not accounted for in that linear model. Okay? And so in this work, in order to get a conservative model here, we had to check the distribution of these parameters. The bias and gradient, they will be constant over the duration of validity of our error model. So we took data over 30 minutes to make sure that these parameters were constant. And so the residual error captures the rest, the remainder of the error. Okay? So the bias parameter, we can use overbounding to find its variance. And this is the URA parameter that is used in ARAIM. And then for the gradient and residual error, we had to process data ourselves. So we processed 9 months of data for Block 2F satellites, a total of 500,000 data points. We've processed much more data since then, since the paper was submitted. And we use that to determine the distribution of bias, gradient, and residual error parameters. I have examples here for the residual error parameters. You have the residual orbit radial error component and the orbit in-track error component. There's also a cross-track component. The reason we had to look at these components individually is that, and this is in the local frame of the satellite, the problem is the orbit error is going to project differently at different locations on Earth. You can find details of that in the paper, but what we did is there's a little bit more math behind that in order to find an error model that would account for the worst case location on Earth of a user receiver, okay? To take the worst case projection of these errors. All right, so what you're seeing here is kind of a representation of how we apply overbounding. And so let me get my pen here. So this is really a CDF, the traditional CDF that you're used to seeing. You're used to seeing it like this, goes from 0 probability to 1 versus the x-axis being your error. I'm trying to draw, I'm hoping you can see this. And it doesn't look like this here because my y-axis is a log scale, and then it's not really a CDF, it's a folded CDF. So to the left of the red line I just drew, we have the CDF in log scale, and to the right is 1 minus CDF. Okay, and this way I can simply upper bound my empirical distribution, which is shown in blue, with my Gaussian overbound, which is shown in red. And the resulting sigma is the standard deviation of the overbounding function. All right, for the purists, there are lots of details that we need to add to that, but that is basically the idea behind it. I'm happy to talk about this later. How does all this come together? Well, let's rewrite our measurement equation. So we have our carrier phase measurements for all satellites at all 3 time steps, and the carrier smooth code measurements at all 3 time steps that are stacked in a single measurement vector. That's our Z. And if you remember from the early slides, we were expressing Z as age. Wow, I didn't know it would take so long. This is our age X plus V plus V. Okay, so we've kept the original form that we wanted to achieve. And so the age matrix here is made of the geometry information. There's a matrix for the cycle ambiguity components, basically zeros and ones. Cycle ambiguities are constant over time. And the error parameters, coefficients, those error parameters are also constant over time. They're made of the bias and gradient parameters that we used to model the change in the satellite orbit and clock, okay? And then probably the trickiest part is how do we deal with the measurement noise vector? So the off-diagonal vectors or the diagonal vectors, you know, we have models to deal with these, but then we must also take into account the correlation between these measurements because, so these off-diagonal components, because the tropo and the orbit ephemeris and clock that are impacting the carrier measurements are also impacting the carrier smooth code measurements. And even more than that, remember that we are actually using, in the carrier smooth code measurement, we are using carrier measurements that show up in the top part here of the matrix. So there is correlation just because of that. But fortunately, the smoothing process is a well-structured process. So we were able to derive analytical expressions for the correlation between the carrier smooth code measurements at current time, 5 minutes ago, 10 minutes ago, and the carrier smooth code measurements at current time, 5 minutes ago, 10 minutes ago. Okay, so all of that is conservatively accounted for when we write this down. So we are not double counting information here. All right, one more thing. Yeah, the last term here, B, in my equation, how is it dealt with? Well, in a very similar way as it is in the baseline algorithm. We basically take the worst conspiring bias. And so similar to the baseline A-RAIM algorithm, we can bound the vertical positioning bias, the impact of the bias on the vertical positioning error, by putting absolute values on the estimator coefficients. We have a matrix A to account for the fact that a large source of error in that bounded bias comes from signal deformation, which only impacts the code, the carrier smooth code measurement. It won't impact the carrier measurements. So that's why we have a scaling factor here. But again, we tried, in our many iterations, we tried many of these models, and this is what we ended up with. All right, a few more considerations. Again, we are using identical algorithms to what is used in ARAIM, and that is part of the choices, is part of the explication for the choices we made to use batch ARAIM. We do have to guarantee the validity of the error models that we are using over time. This is new. This was not dealt with in ARAIM. And so we have more work that we've been doing, that we are currently doing on modeling those, basically the time correlation of the errors over time. And so this, in this approach here, it corresponds to the parameter sigma. I can't see the part of my screen, but parameter sigma GE and the sigma residual, we have to validate these. And then we have to transmit these new parameters to the user. So there are two approaches. One is to hard code that on the receivers, the way it is done for RAIM. It's not quite the ARAIM philosophy. So another way is to simply incorporate that in the integrity support message. And it's good to know that there is a time correlation parameter right now in ARAIM. It's not meant to be used for this, but there may be ways to transmit that information. This is something that would have to be investigated. All right. So I have 5 more minutes to kind of go over some analysis and performance evaluation. I start with a non-conventional configuration for ARAIM, where we assume that the probability of constellation fault is very low, is 10 to the minus 8. This is not the current assumption in ARAIM, and we would have to implement some sort of other monitor to make sure that this is the case. And then we assume a small alert limit as compared to what is currently assumed and what is required in LPV 200 requirements. The reason we did that is we wanted to emphasize differences between snapshot ARAIM, the baseline algorithm, versus our batch ARAIM approach. And to start with, we looked at performance at a single location, at an example location of Chicago. And I guess the first part was really, are our error models really consistent with ARAIM? And so what I'm showing you here are standard deviations for snapshot ARAIM in black, so the baseline, and the new method in red. And in parallel, we have the bounded bias contribution, also black and red for snapshot versus batch. And from analytical results that we derived in a previous paper, or in the conference paper that is related to this, we could show that if the error models were consistent, we should get the same position domain variances and standard deviations if we take a batch period of 200 seconds and if we freeze the geometry. What we mean by freeze the geometry is don't let the satellites move. Okay, so if we freeze the geometry, we are not leveraging satellite motion, and what we get from hatch filters in snapshot ARAIM should be the same as what we get from the batch in our new approach. Okay, and as you can see, yes, they match. So good job. That was confirmation, at least, that we were properly accounted for the correlation between Fourier smooth code and carrier, that our measurement error models over time were not introducing some inconsistency between the approaches. What if we unfreeze those satellites? Let them move, okay? Now you see the impact of satellite motion. Okay, you can see especially in the peaks that the standard deviations decrease significantly. Okay, so compare having no satellite motion with satellite motion. Wow, significant decrease, especially at the peaks. This will make a big difference in terms of availability. And the same, by the way, for the bounded bias. So I keep increasing the batch period. I can actually do that. I can increase the batch period for as long as my measurement error models are valid, and for as long as, you know, operationally, I can ensure that my receiver will be on. And so if we increase this to 10 minutes, well, this is the result. We can also look, I should have mentioned, we've done this analysis over 24 hours. Why 24 hours? Well, I go back sitting on my GPS antenna, look up in the sky. I look up now and I look up tomorrow, 24 hours later, I will have the same distribution of satellites. So the GPS satellite constellation repeatability period is 24 hours. That's why we consider that number. Of course, Galileo is in there. It makes things a bit complicated, more complicated, but 24 hours is good enough for this analysis. All right, sorry for that parenthesis. Going back to my chart, I have risk here, log scale versus 24 hours. And the snapshot approach, you can see these big peaks well above the 10 to the minus 7 requirement. And then I look at my batch approach, which are these red and blue lines, and it's much lower. You can note that we have two of these batch approaches, and you can see the details in the paper. As I mentioned, there were several iterations of this paper, and we came up with several implementations. That's really a detail. Okay, so it already looks like my batch approach will be much better than the snapshot approach because I'm reducing all these peaks of risk. Now I can further analyze performance by looking at availability. Availability is a percentage of time where my risk bound in red or black here is lower than the requirement, again, the 10 to the minus 7 that I have here. Okay, so I look at this percentage of time and now I get the number, the availability number over many locations. And so availability here is color-coded from red to blue, from 80% to 100%. And yes, you can see the difference. This is snapshot ARAIM to the left, batch ARAIM to the right. Obviously, batch ARAIM is much better. By the way, it's not perfect. You can see that there are lots of locations where we don't quite reach 100% availability. We're probably closer to 95 or even lower availability. But still, we took this configuration to emphasize the difference between the two, and it makes it pretty obvious here. All right, let's go back to a more conventional configuration for ARAIM that you can see being investigated in the previous milestone reports. And we go back to a probability of constellation fault of 10 to the minus 4. That is the nominal value that we assume in ARAIM, an alert limit of 35 meters in the vertical direction, which is the LPV 200 requirement. And we consider a depleted constellation. So the nominal GPS constellation has 24 satellites, and we removed one. Same for Galileo. We'll remove one to account for outages, potential outages, and see the performance in these cases. And this is what we get. So on the left-hand side, you have snapshot ARAIM. Availability is here is color-coded, 95% to 100%. But we knew we did not have 100% coverage for snapshot ARAIM from prior analysis. That's why we are now looking at this. And then we have batch ARAIM on the right. We have much more blue, better performance. And in the paper, you will see we have tabulated many more results. We can just briefly look at that. Oh, I should define the coverage. So coverage is the percentage of location where we achieve a certain level of availability. For example, the percentage of locations where we achieve, say, 99.5 availability. Okay, so that's the percentage of location where we have that dark blue color. That's what we call coverage. And so we look at coverage of 99.5% availability, coverage of 95% availability in parentheses. So these are the two numbers that you see, 99.5, 95%. And here for the nominal constellations, with nominal values, snapshot ARAIM does very well. Okay, there would not be a need for batch ARAIM in this case. But for depleted constellations, well, we knew that we were going to encounter some issues. We don't quite have a high availability number if we look at, or a high coverage number. If we look at batch ARAIM, we've improved that robustness of the availability in this case. And if we increase the batch period to 20 minutes, we can get above the 95% coverage number that may be desired. So you can find more results like this in the paper. Okay, conclusion. I have one more slide after that, and then I'm done. Yes, exploiting satellite motion in ARAIM can improve robustness of availability for LPV 200 requirements. We've seen that for depleted constellations. And we were trying to set a path towards tighter alert limits. And they may be achievable if we find a way of dealing with the constellation faults, maybe using additional constellations. So that's open. And then we designed a computationally efficient batch ARAIM estimator and fault detector that does both the code noise averaging, we're still using those hatch filters, and it uses satellite motion using these additional carrier phase measurements. All right, yes, these estimators and detectors also incorporate the error models, and these error models, we've derived new ones for GPS, orbit, and clock, troposphere, multipath. And these models are consistent with ARAIM, and they account for the dynamics of the error over time. And we've started validating them using historical data. All right, that last point really was the most challenging and the one we wanted to work on more. I've shown you this bias plus ramp model, but this really only works for the orbit and clock. If we wanted to really, I guess our desire was to get a more general approach to this. And to do this, we went back to Steve Lenger's PhD work, who kind of worked on how to conservatively account for the time correlation of the errors if this was uncertain. And so we derived time domain solutions to this problem, again, based on Steve Lenger's work. For example, here on the top right-hand side chart, again, this is hidden for me, but what you see, the many different color curves, they are for empirical data for radial and clock components of the ephemeris errors. And these are for different satellites, the different colors. And you can see that we have upper and lower bounds on these autocorrelation functions that we can use in an estimator to conservatively account for the time correlation. We need both an upper and a lower bound on the errors. And these models are first order Gauss-Markov processes, so they can easily be incorporated into an estimator, like a batch estimator or a Kalman filter by state augmentation. And there were some limitations, however, to these time domain approaches. So we are now working on frequency domain approaches. This is again, these curves have been provided by Elisa Gallon at IIT. And so here she processed a year of tropospheric data at 20 locations around the Earth. And we plotted the power spectral density, and we can derive a bound on those power spectral densities, again, using a first order Gauss-Markov process. And we have proved that this would provide a bound on the variance of the position estimate. So again, bounds over time derived at the measurement level guarantee bounds on the position estimation error variance. Okay, and so we are now working on Kalman filtering with integrity for GNSS inertial integration. This is where we're going. All right, I probably talked too much. I want to thank you. I would like to thank the FAA. And I would like to mention that the opinions that we express in this paper are ours, and they're not necessarily shared by the FAA. Thank you very much. And I will now switch to, I will maybe sit. And I will check the questions and answer. Rick, I don't know if you want to take over or if I can just do this by myself.
No, go right ahead.
All right, thank you. From Mike Miller. How are you? I would think the alert box for an autonomous car would be better than 10 centimeters, not 1 meter. Thoughts? Excellent question, Mike Miller. I miss seeing you at conferences. It's kind of strange like that. But yes, so there is a paper by Tyler Reed when he was at Ford, he actually did some work trying to determine what the size should be. And he came up with the numbers around 30 centimeters for residential areas and 70 centimeters for highway environments. And so there's quite a bit of engineering, design, and trade-offs that he had to take into account to come up with these numbers. But that's what he came up with. You can check the paper or send me an email, and I will forward the paper to you. Okay, next question. Are you using divergence-free dual frequency smoothing? Ooh. Yes, for smoothing code with carrier. Am I using divergence-free? No, I'm using iono-free. I hope that answers the question. So the problem with the iono is not so much, I guess, under nominal condition to model it, but over time, monitoring against iono faults, it becomes a real headache. So we better not try to fix cycle ambiguities and use iono-free measurements, then try to use other combinations of multiple frequencies and try to model the iono or try to detect it. I hope that makes sense. So we want to get rid of the iono, so iono-free. Thomas Pani, hello, how are you? Are there special requirements regarding carrier phase cycle sleep? Excellent question. Cycle sleep detection for batch ARAIM. Yes, this is an open problem, something that will have to be addressed. And so in this work for now, we've assumed that cycle ambiguities were detected and repaired. And that's certainly one area that needs to be addressed further. It's an excellent question. I think you've touched at the, one of the most crucial pieces of this work. But by the way, a detected cycle sleep will also cause the hatch filter to be reset. So this is something that would even have impact on the baseline algorithm. So excellent question, thank you for this. to help so from Stephen Ching, to help myself to rationalize the concept is exploiting the satellite motion, meaning using these additional inputs over time to create and use some kind of error model bounding to reduce the orbit and clock errors. So, trying to interpret what you're saying, no, the goal is not to estimate the error model's dynamics. The goal is really to exploit the motion of the satellite. The change in the geometry provides observability on constant parameters, such as cycle ambiguities. And so it's not quite the same process. And so even though we may get observability on the bias and gradients parameters that are used to model the orbit and clock, this is not why we do this. This is not the primary goal. Maybe like a secondary point. Garrett Shook. I hope I answered. I have no way to check, I guess, but you can always write to me. If you were to assume 27 or 30 satellite constellation of one type, GPS, would the method still work? Yes. In other words, does this method still require multi-constellation signals if the constellation is more robust than 24 satellites? Again, a great question. So early on, I had tried to, when I was doing my work for my PhD thesis on GPS Iridium, I was trying to look at the performance with GPS only, and really didn't make much of a difference. So having a second constellation, I don't know exactly where the knee is, in the curve for, performance improvement versus number of satellites. But GPS alone, I think it's just not enough, even with 27 or 30 satellites. That is something that would be worth looking at again with what we know now. But I have little hope. It's a good question, though. Thank you. The batch approach appears to require storing a lot of information. Can current GNSS receivers accommodate this? Good question. I think we can make arrangement to reduce that. So the goal here was to evaluate the performance. We wanted to, be close to something that could be at least tractable on an avionics receiver. So I'm not sure what to tell you. I think we can improve the computational efficiency of this approach. I don't know how much storage we need really. If we keep measurements 5 minutes ago, 10 minutes ago, the fact that we picked 5 minutes and 10 minutes ago doesn't have to be a hard, the 5 minutes period itself is not a requirement. We could move that. And if, we could find ways to make this more computationally efficient. That's how we would say it. What is for sure, it's that it's going to be a little bit more computationally expensive than baseline A-RAIM. So that's it, I guess, yeah.
Well, great. Well, thank you, Matthew, for your time. We appreciate your presentation. We've had wonderful participation and attendance today. Matthew, thank you for your time. And again, these slides and video will be made available on the ION website later today.